Hi everyone. Lecture 5a of Differential Equations and Linear Algebra is going to mostly be an in-depth mathematical analysis of a very important model from physics, free fall under the influence of the Earth's gravity, both with and without air resistance. We're going to talk about one-dimensional up-down motion here, not side-to-side two-dimensional projectile motion, because we want to keep things as simple as possible here in our initial model. We'll also talk about slope fields and Euler's method to review those topics from the last couple of lectures as they seem helpful for our analysis. It's going to be very important here, this is a real big deal to pay attention to keep track of what quantities, what letters represent constants and what letters, quantities represent variables when we're doing our mathematical analysis. But another important thing to keep in mind is that later on, we're going to change our perspective with some of the constants and allow them to be variables. Now that seems kind of contradictory. How can a constant be a variable? But I'm going to tell you it's first of all very useful, and secondly it's certainly something you can do. Whether a letter represents a constant or a variable is all in your head. It's all in how you are thinking about it. And it's important to be flexible. It's going to help us solve infinitely many problems at once, in fact. In Lecture 5b, it's the linear algebra topics. We're going to talk about the important idea of a projection of one vector along another, and we'll talk about another physics application, actually, for that. Projections are essentially applications of dot products and normalization from Lecture 4b. Then we'll look at systems of linear equations in two dimensions, an example or two, talk about the method of elimination, and try to summarize the main things that happen with such systems. But let's get on to our physical model of free fall under gravity without air resistance, okay, to keep things as simple as possible here initially. It's important to define your quantities, your letters. Y is going to be the height of some object above the ground, say, in meters. It's going to be positive when you're above ground, and in fact, if you go higher, it's going to get more positive. If we drill the hole in the ground and let it go underground, then y could be negative. So y could be positive or negative, but mostly we're going to think of it as positive here. In meters. It's an object of mass m in kilograms. We're not saying what kind of object it is here. Could be a rock, could be a feather. Assuming no air resistance doesn't sound like a good idea for a feather, unless it were in a vacuum. But we want to keep things simple here and start with no air resistance. And t is time in seconds. What's the goal? The goal is to find how y depends on t. Y is a function of t. What is that function? Why do we want to do that? Because it helps us solve problems, practical problems in physical situations, and we'll look at such examples here. We need to make an assumption that is borne out by experiments, and that assumption is that the force due to gravity is approximately constant. Now that's not precisely true, to tell you the truth. It gets more pronounced as not true the further you go away from the surface of the Earth, like if you're in space, for example. But near the surface of the Earth, the force due to gravity is approximately constant, and that constant is typically written in this way. The force due to gravity is negative mg, where g is the acceleration due to gravity near the surface of the Earth, which is approximately 9.8 meters per second, which is often called meters per second squared. Okay, so we're assuming this is true. I'm not proving this is true. This is something you'd have to verify with experiments. Why is there a negative sign here? The reason is because y, the positive direction for the height, is upward, but the force due to gravity is downward. It's directional. It really is, in a sense, a one-dimensional vector, though I won't say any more about that at the moment. It's got a direction to it, the opposite direction as the positive direction. So we need the minus sign there. Its magnitude, its size, would just be m times g without a minus sign. But the force itself includes the minus sign. If a is the acceleration of the object, as an upward acceleration, so positive if you are speeding up as you go up or slowing down as you go down, Newton's second law, here's the physics, which says F equals ma, becomes this equation in this situation. Here's the part where F equals ma, force equals mass times acceleration. This part over here is essentially the nature of the force that I was talking about here. It's a constant that can be written as negative mg. Okay? So this is our equation of motion that comes from Newton's second law. What can we do with it? Well, we can cancel the m's. And what that's going to say right away is that when there's no air resistance, the mass doesn't matter. If you're letting a rock fall in a vacuum or a feather fall in a vacuum, the model says they fall at the same rate. Y is the same function of t if the initial conditions are the same, if the initial height and initial velocity are the same. So our equation simplifies. The acceleration due to gravity is this negative constant, negative g. That thing really is a differential equation. Why? Because A, the acceleration, is a derivative of y with respect to t. It's, in fact, a second derivative of y with respect to t. It's this. Here is our differential equation modeling the situation. It's called a second order differential equation because the highest degree of a derivative is a second derivative. There's no third derivatives or fourth derivatives, etc. That's called a second order differential equation. How can we solve it? We want to find how y depends on t. We're saying the second derivative is a constant. I hope you know even from Calc 1 and Calc 2 that you should just integrate that constant twice, I guess, to figure out how y depends on t. And that is the strategy, and that is what will work here. However, initially, I'm going to think of this as a first order equation. How? By introducing a new quantity, v, which is dy dt. V is the velocity. Also positive going upward. In other words, if the object is moving upwards, the velocity is positive, and if the object is moving downwards, the velocity is negative. Just replace that second derivative of y with respect to t with a first derivative of v with respect to t. It's an equivalent equation. These two equations, even though they are technically different looking equations because they involve different dependent variables, y versus v, are equivalently mean the same thing because the first derivative of v is the second derivative of y, all with respect to time t. It's first order because the highest degree of a derivative in this equation is a first derivative. Again, keep in mind the goal. The goal is to find y as a function of t. Initially, we're going to find v as a function of t, once again, just by integrating. This is what I called a pure antiderivative problem. In this case, it's dv dt. Well, it's this constant, negative g. You could think that as a function of time t, although it's a constant function of time. You don't see any t's there. We also could think of it as a constant function of the dependent variable and call it an autonomous equation as well. But it's going to be more natural, better, to think of it as a constant function of t in this case. We can just integrate to find a general solution. V is going to be the integral of negative g with respect to t, which is going to give you, in general, negative gt plus c, where c is an arbitrary constant. This is again called a general solution. What that means is that, well, first of all, it is a solution of the differential equation. No matter what c is, c can be anything. That's pretty obvious if you differentiate this with respect to t. If you find dv dt, you are going to get negative g. No matter what c is, and in fact, no matter what t is. It also represents all possible solutions. Any solution of this differential equation can be put in this form for some value of c. I'm going to change my perspective here, and now imagine what I call an IVP, or initial value problem, with initial velocity v of 0 equal to some specific number v sub 0. That's another subtle point here. Sometimes our constants are arbitrary. Sometimes our constants are imagined to be specific. So here I'm imagining c to be arbitrary. Here I'm imagining v0 to be something specific. I'm not saying what it is, and it could be anything. I'm just imagining it to be something specific because it's going to give us a unique solution of the initial value problem. And that can be found by just solving for c. If you replace v with v0 and t with 0, and solve for c, that you see that c equals v0. We need to choose c to be the initial velocity in order to get the unique solution of the initial value problem. Imagine this is representing infinitely many answers, and I'm imagining this representing one specific answer, though again, v could be anything. But I'm imagining it's fixed in my mind. This equation does give us the velocity as a function of time. It's actually also a differential equation because v is dy dt. That v right there is dy dt. It's a first order differential equation that can be solved by direct integration again. It's also a pure antiderivative. Now you really see a function of t over here. And there's no plain v's. It does not involve the dependent variable, unlike some of the other differential equations that we've looked at. So integrate negative gt plus v0 to get y as a function of t. And the general solution is that y equals this, where c can be anything. Right? Integrate this, you're going to get negative g over 2 t squared plus v0 times t plus some arbitrary constant c. Once again, I can add an initial condition in there to think about initial value problem. Now I'm imagining the initial height, y0, to be fixed. And the unique solution turns out to equal this. The c actually equals y0 in this case. Okay? It doesn't always happen that c is the initial value. In fact, an example we looked at in lecture 4a, it did not happen. That was the logistic model. C was not the same as the initial population there. But in this model, it does happen to be. Here is how y depends on t. This is the unique solution, not only of this differential equation, but also the original second order equation. And then this can be used to solve practical problems, although different people have different ideas of what's practical. So this is your turn. This is where you want to pause the video, try to solve this problem on your own. You could certainly solve it using the numbers that you see there. A mass of 1 kilogram, initial upward velocity of 20 meters per second, so you're throwing the object upwards, straight upwards at the start, from a height of 1.5 meters, which is about this high from my floor here, close to 2 meters high. So you can certainly plug in those numbers right away to find the maximum height of the ball, and here I'm saying it's a ball. Okay, the object is a ball. The maximum height of the ball and the time to come back down and hit the ground. So go ahead and pause the video to work on that. I'm going to show you, I'm assuming you're back now. I'm going to show you that if you think about this in the right way, you can solve infinitely many problems at once. If you treat things as constants, and then ultimately even treat those constants as variables, you'll get some insight, some interesting and informative insight into stuff. So here I'm just emphasizing we could plug numbers in right away, but we can also solve infinitely many problems at once. It's amazing how powerful. By doing the general case before plugging in the numbers. And then, again, we'll gain more insight by thinking of those constants as being variables and making graphs related to them. You'll see what I mean when we get there. What about for the max height? The maximum height occurs when the velocity is 0. Okay, so you throw this ball upward with an initial velocity of 20 meters per second. It reaches the peak at the moment in time when the velocity is 0. Okay, because it's going up at first with positive velocity, then it reaches the peak at some instant in time, and then it comes back down and it has a negative velocity. So set the velocity equal to 0 and solve for t. And I get t sub max, I'm labeling it just to emphasize that it's the time where the maximum occurs. The subscript max is optional here. It's really just a label. Don't let it bother you. Is v0 over g, right? Because you add gt to both sides to cancel on the left side, and you get a gt on the right. Then you would divide both sides by g to solve for t. Again, I'm just calling it t max. It turns out to be 2.04 seconds. You should have your calculator out and check these numbers as well. When you plug in, v0 is 20 and g is 9.8. But I could think of this as a function of v0 if I wanted to, and graph it as a function of v0. Or I could even think of g as a variable And that might be useful if I'm thinking about throwing the same ball on the moon or on Mars or something like that. The maximum height is found by plugging the time where the maximum height occurs into the height function. And again, I'm calling it y max. The max is optional, okay? I'm just emphasizing it is the y coordinate of the maximum point. The graph of y versus time is going to be some downward opening parabola. I hope that makes sense, that that's what the graph of y versus time looks like. T max is the specific number right here where you reach the peak, and the second coordinate of that point would be y max. This right here would be y max. Plug it in, simplify. You should double check that it simplifies to this right here, which I could combine into one fraction, but there's really no reason to. And keeping it like this also emphasizes that when the initial height is 0, if you are shooting it upward from ground level at the start, the maximum height is just this, which is a simpler looking expression. If you plug the numbers in, you get 21.91 meters. But once again, I could think of it as a function of v0, and I could think of it as a function of y0, and I could graph those functions and get some insight. For the time to hit the ground, we need to set the height equal to 0. The ground is height 0. So set that equal to 0 and solve for t. T hit. Maybe it would have been better to call that t ground. By hit, I mean hit the ground. It's a quadratic function of t. I need the quadratic formula. T is equal to negative b. The b would be v0. Negative of that is this thing right there. Plus or minus. I purposely did not put a plus or minus there. Why not? And why would I put a minus sign there? Would this make the time negative? No, actually, because there's a minus sign down here. Putting the minus sign there makes this positive. I could have put a plus or minus at the beginning and decided which one to take at the end, but I knew it was going to be the minus sign. So that's negative b minus, in this case, square root of b squared minus 4ac. A is coefficient of t squared, negative g over 2. C, the constant term, is y0. All over 2 times a. A, again, is negative g over 2, so I get a negative g over 2 there. And again, the negative signs cancel out, leaving me with plus signs. This is how the time when it hits the ground depends on v0 and g and y0. And again, if y0 is 0, this term would go away, and the square root of v0 squared, because v0 is positive, or at least if v0 is positive, as it would be if you're going upward from the ground, is going to be v0 itself. And this would simplify to 2v0 over g when y0 is 0. If y0 is 0, you're shooting it upward from ground level, the t hit is going to simplify to 2v0 over g. Again, because this term's going to go away. The square root of v0 squared in general is the absolute value of v0. But v0 is positive here, so that would be v0 itself. You have another v0 there, you get 2v0 over g in the case where that happens. But that's not the situation here. The situation is y0 is 1.5. So you plug the numbers in, you should get 4.16 seconds. Yeah, this benefit. Solving infinitely many problems at once. You can graph how the solutions depend on these constants, but they're no longer constants in your mind, at least. It might be interesting and informative to plot the time to hit the ground, t hit, either as a function of v0 or y0. If I want to do it as a function of y0, I need to pick something specific for v0, like 20, but then keep y0 arbitrary, and I'd get this graph. Notice how the axes are labeled. The horizontal axis is y0, the vertical axis is t hit. Our particular example is when y0 is 1.5, way down here, t hit is just barely above 4. I forgot what it was, just a little bit above 4. But the interesting thing to think about here is that while you could use this equation and this graph to make other predictions for how long it's going to take to hit the ground, based on the same initial upward velocity, but different initial heights. For example, at an initial height of 60, and an initial upward velocity of 20 meters per second, it's going to take about close to 6 seconds to hit the ground, okay? I'm not claiming my drawing is perfect. It's also interesting to note that the graph's not straight, it's not a linear function, and in fact it's increasing in concave down. What would that mean, the fact that it's concave down? The fact that it's increasing means the higher you go, the longer it's going to take to hit the ground. That's pretty obvious physically. But what's the practical meaning of the fact that this is concave down? It means for any given change in the initial height when the height is small, the corresponding change in time to hit the ground is going to be relatively large. On the other hand, for the same change in height when the height is large, we have a smaller change in the time. That should make some intuitive sense too. This ball doesn't really go up much before it starts coming back down. And so changing the height when your height is already pretty high to begin with is not going to change the time when it hits the ground very much. On the other hand, we can think of this as a function of v0, set y0 equal to something specific, and get this thing. That one looks linear. Careful, it's not. I mean, the equation itself is obviously seemingly nonlinear. And if you look carefully at the graph, you can see it curves here. In fact, the graph is not straight. Looks are deceiving. Even over here, the graph's not exactly straight. This graph is actually always increasing and concave up. Just the concavity, the positive concavity is very close to 0 over here. But it's almost straight, you might say. And if it were straight and went to the origin, it would be a direct proportionality. So in effect, once the initial velocity, this is supposed to be a v0 that you can't quite see, once that initial velocity is high enough, essentially the time to hit is proportional to it. If you double a high enough initial velocity, the time to hit the ground will essentially double. Okay? But it's not exactly. And here it's more pronounced near the bottom. In our example, v0 was 20. And again, the time to hit the ground was a little bit bigger than 4. All right, now let's bring error resistance into play. This does make it harder. For one thing, it's harder right at the start, like how do you bring error resistance into play? And for another thing, it's harder after the start because the differential equation is more complicated and harder to solve. Assume there is error resistance. First question, what is the nature of the force due to error resistance, sometimes called drag? We might have to hypothesize a form to the error resistance force and then match it with experiment and see how well it matches. And if it doesn't match very well, we need to modify our assumed force due to error resistance. But we might as well start simple. In general, it can be complicated, partially because objects like feathers are not shaped like balls are. So this can be complicated. As a first approximation, let's assume the force due to error resistance is proportional to the velocity and in the opposite direction. If it's a positive velocity, the object's moving upward, the force due to error resistance is going to be downward. And the bigger the velocity is, the more wind the object feels, so to speak, the bigger the error resistance should be. On the other hand, if the velocity is down, negative, error resistance should point in the positive direction. And once again, be large in magnitude if the velocity is large in magnitude, and small if the velocity is small in magnitude. So we're going to assume the force due to error resistance is a negative constant times the velocity. For some k that's positive, the negative k is the constant of proportionality. K itself is positive. I didn't have to do it that way. This came up in another example in like lecture 2 or 3 as well. I could just call this k times v where k is negative. Okay, but I'm kind of trying to emphasize that it's negative by writing it this way. So what's our model? We need Newton's second law again, F equals ma. And we need to realize that forces, distinct forces, add. And that actually works whether you're thinking of the force as a scalar quantity or a vector quantity. They add. We've been talking about vectors recently. We'll talk about them more today in lecture B. they add. So I get something like this. The force that's total force is the sum of the gravitational force and the force due to air resistance, which, since both F grav and F air have negative signs involved, is negative mg minus kv. That must equal ma. That's Newton's second law. That right there is N2 for Newton's second law. But we want to relate this to differential equations as well, so that's m times dv dt. M does not cancel if you assume there's air resistance, at least if you assume the air resistance is of this form. The mass does matter. The shape also matters, and that's where it gets extra complicated, but we won't get into that. A more standard way to write this is to divide both sides by m, though it doesn't completely cancel. Cancels on the left, and on the right you get negative g minus k over m times v. On the left you're left with dv dt. This is our first order differential equation. You see a v on the right side, the dependent variable, not t. I want to think of this as an f of v function. I want to think of this differential equation as autonomous. It's a very different kind of situation. It's not a pure antiderivative problem. We can't just integrate. So what do? You can separate variables here. We talked about separation of variables before. Pretend dv dt is a fraction. Get all the v's on one side and the t's on the other side. Get all the v's on the left. There's just a v right there and a dv up there. Get all the t's on the right, the dt on the right. In other words, divide both sides by negative g minus k over mv, and also, quote-unquote, multiply both sides by dt. That's not rigorous math. I did more fully justified a couple lectures ago. If you do that, and if you then multiply the resulting fraction on the left, on the top and bottom by m, you'll see that it gets to this form. Initially, I would have a 1 over negative g minus k over mv down here, but then I can multiply the top and the bottom by m so that I don't have fractions within fractions. And then you can integrate both sides to solve this. And it is doable. It's not too hard. The right side is easy to do. T plus C1. The left side is a bit more complicated, but it actually can be solved by guessing. The guess that you should guess is negative m over k natural log of the absolute value of negative mg minus kv. And that's going to equal t plus c1. And my pen gets all funny over here. I don't know why. T plus c1. That's a v in there. I'm going to stop at that step. I will tell you that it is advantageous, not absolutely necessary, but advantageous to replace the minus signs in here with plus signs, which you can do because there's absolute value signs around it. You would want to multiply both sides by negative k over m, get it on the right, and maybe instead of calling that c1, you'd call it c2 after that point. And then you'd want to get rid of the logarithm by exponentiation, and you'd want to solve for v. I'll leave the steps to you. Here's the answer you should get if you replace this in here with mg plus kv. You should get this. V as a function of t is this function of t. I'm using an extra label in here. Phi sub v0 of t is the solution function name, phi sub v0. I have done this in recent lectures. It's not necessary to do that, but we will find it helpful. It emphasizes the initial condition, the initial velocity is v sub 0, and it also emphasizes it's a function of t. I also am remarking that it does equal dy dt, and this dy dt equals this would be yet another differential equation that would be a pure antiderivative problem. You don't see any y's over here. I could solve for y as a function of t by integrating that. Just integrating. I'm not going to, because it's going to be messy, but it could be done. I'd rather do something else. I'd rather now use this model to also predict when the object would hit the ground based on this model. And well, I was going to do the work on the board, but I think for the sake of time I won't. This could be a good exercise for you if you want to pause the video right now. I'm going to imagine setting this equal to 0 and solving for t to figure out the maximum height, time when it reaches the maximum height. Then I could plug into y to figure out the actual maximum height, which I'm not going to do. So I'm just going to focus on the time when it reaches the maximum height. So set this equal to 0, solve for t. I'd add mg over k to both sides. I'd divide both sides by this. I'd take the natural log of both sides. In the end, if you do that, you should check that you're going to get this thing right here. The time of the maximum height is this. And again, the max label subscript is optional. Don't let it confuse you. I'm just using it to emphasize, hey, this is the time when the maximum height is reached according to this model. M, K, G, and V0 are all constants, but I could go ahead and change my perspective and think of them as variables if I want, and in fact I'm going to do that. I'm going to think of V0, the initial velocity, as a variable. I am going to set m to be 1 and k to be 1. 1 kilogram for the mass. The units for k turn out to be newtons per meter per second. Don't worry about the meaning of that. We could then graph it as a function of V0, and here's the graph that you would get in blue. The blue graph is the graph of this function right here. Notice there's an extra graph in there as well. I'll explain in a minute here. The time to reach the maximum height for this model as a function of V0, the initial upward velocity, positive if you throw it upward, negative if you throw it downward to begin with. But we are only thinking about when V0 is greater than or equal to 0 here. Is this function of the initial velocity? It's an increasing function, meaning the bigger V0 is, the faster you throw it upward, the longer it takes to hit the ground, or to reach the maximum and hit the ground. But it's a concave down function, diminishing returns. When V0 is small, a given increase in the initial velocity, like a doubling of it, will cause a relatively large increase in the time to reach the maximum height. On the other hand, when V0 is large, that same change in V0, don't think of it as doubling, but think of it as the same change, like add 1 to it, will produce a smaller change in the time to reach the maximum height. If it's already going upward fast to begin with, increasing the speed a little bit more doesn't change the maximum height much more, according to this model. This point right there, 21.11, turns out to be our prediction in a situation where the initial upward velocity is 20 meters per second. We predict it'll reach the maximum height in 1.11 seconds. This point right there was the prediction for the, based on the initial velocity, for when you reach the maximum height for the model with no air resistance, 2.04 seconds. This expression, V0 over G, was that thing that I mentioned about 15 minutes ago that you could imagine to be a function of V0. And if 1 divided by 9.8 is about 0.102, this would be 0.102 V0. A linear function, in fact, a proportionality, when there's no air resistance. Vastly different predictions, really. Which one's right? You'd have to compare. Perhaps neither of them is right. Though I would venture a guess that maybe especially for a feather, this one would be more likely to be right. Though for a feather, k is not necessarily 1. It could be something else. In the no air resistance case, we got t to be 2.04 seconds. You can go check that again. Okay, so this is solving infinitely many problems all at once, because you've got a function that you can use infinitely many times if you had the time. And you can think about its behavior. It's really cool, I think. Okay? Maybe you don't think it's cool. I think it's really cool. Conceivably very useful if you're thinking about projectile motion for some reason. Like if you work for the military or something. One-dimensional free fall, under gravity with air resistance again, we're continuing. But now we're going to think about the slope field. Do the solutions for the various initial velocities make sense if we think in terms of the slope field of the autonomous ODE. Again, ODE means ordinary differential equation. Here again is the differential equation. It is autonomous because the right-hand side depends just on the dependent variable v, no t's on the right. And if you plug in g is 9.8 and k and m are 1, you get this simplification. What would the slope field of that look like? How could you make it? Remember what we said about slope fields. For any given point in the slope field, whose axes you'd want to label t and v here, take the point, for example, whose coordinates are, oh, I don't know, 2, 5. Plug that point into the right-hand side function, f of v. In other words, plug 5 in. We don't need to plug 2 in because there's no t on the right-hand side. And that would give you f of 5 would be negative 9.8 minus 5, which is negative 14.8. And then draw a little line segment through that point, centered on that point, with that slope. It's going to be pretty steep. Do that for all points in the plane. Ha ha ha. Of course, you can't do it for all points in the plane, but you can do it for some points, and you can get technology to do it for more. And this is a typo here. This does not have constant slopes along vertical lines. It has constant slopes along horizontal lines. Let's change that right away. That's what happens for autonomous equations. Along any horizontal line, the slope of the line segments in the slope field are going to be constants. When v is 20, the slopes are all negative 29.8. When v is 10, they're all negative 19.8. When v is 0, they're all negative 9.8. When v is negative 20, they're all negative 9.8 plus 20 is positive 10.2 are the slopes of these little line segments down here. And why did I plug in negative 10 here instead of negative 9.8? Because if you plug in negative 9.8 into this function, you get 0. If f of v is negative 9.8 minus v, if I plug in negative 9.8 into that, I get negative 9.8 minus negative 9.8, which is plus 9.8, which is 0. The slope field has horizontal line segments with a slope of 0 along the horizontal line at v equals negative 9.8. And in fact, that line is what I've called an equilibrium solution. I've mentioned that before. It's a constant function. Notice the notation here. This is a phi sub 20 of t, meaning the initial velocity is 20. The graph of our problems, velocity as a function of time, looks like this. It's an exponential decay down to this horizontal line. I'm labeling this phi sub negative 9.8 of t when the initial velocity is negative 9.8. In other words, if you are throwing it downward with that initial velocity, it stays at that same velocity the whole time. It's reached its terminal velocity. Now, of course, if it's going to fall for very long, you'd have to be up high to begin with. I'm going to show you another way to think about this. This other way that I'm going to show you to think about it is very, very important, but confusing at first. Okay, so pay good attention here. I'm going to graph the right-hand side function of the differential equation as a function of v. Can I do such a thing? Of course, if I want. Why not? Or why should I do it? Because we'll see that it's useful. Here it is. V is the horizontal axis in this graph. Over here in the slope field, it's the vertical axis. Here I want to make it the horizontal axis. Not that I couldn't make it the vertical axis. I could. But then I'd be drawing the graph in an unusual way if I did. The vertical axis, is that t? No, it's not t. Well, what is it? I'm labeling it with the function. I probably could label it dv dt, where I'm thinking of dv dt as just one quantity. Maybe it'd be better to call it v prime instead. V prime is probably the best label for that axis. I'm graphing v prime versus v. The derivative of solutions, the slopes of solutions as functions of the current velocity, so to speak. Now the velocity is always changing, right? Except if you're at the equilibrium solution. The velocity is always changing. But at any given moment in time, the velocity is of a particular number. This graph is telling you the corresponding slope. For example, when the velocity is 5, this graph is telling you the slope of the solution curve is around negative 13 or 14 or so. When the velocity is 5, along this horizontal line, all the slope marks have a slope of negative 9.8 minus 5, which would be negative 14.8. That's what the graph's telling you. Notice it's 0 at negative 9.8. Now that looks like it's at 10, negative 10, but it's actually negative 9.8. That's negative 9.8 right there. That's where it crosses the horizontal axis in this graph. It's negative over here and positive over here. Slopes of solutions are negative when v is above negative 9.8 and positive when v is below negative 9.8. Say that again. This graph is negative over here when v is bigger than negative 9.8 and positive over here when v is less than negative 9.8. Slopes of solutions are negative up here when you are above v is negative 9.8 and positive down here when you are below v is negative 9.8. And 0 when v equals negative 9.8, just like this is 0 there. It's going to be very important in coming sections of our differential equations book. What about Euler's method? It's our last main thing to do for lecture 5a. Let's review that. I'm going to go pretty quick. I did a quick overview of Euler's method in 4b. Going to go pretty quick here still as well. My students, you should certainly read about this and check my calculations. What if we preferred just approximating the solution rather than finding its formula? Because you just don't like separation of variables. You always make mistakes with it. Could we just approximate it instead? Yes, you could, though it's not guaranteed to be a good approximation unless you did a lot of steps or used a computer. We can use Euler's method on this initial value problem. dv dt is negative 9.8 minus v, this autonomous differential equation. V of 0 is 20, same initial condition, to approximate the unique solution, which we do know the formula for, and we can simplify the formula for. So I am telling you the answer. This function right here is the unique solution of this IDP here, where I pick v0 to be 20. G is still 9.8, m is still 1, k is still 1. You should double check that it simplifies to this. Which makes sense as t goes to infinity here. This part goes to 0. This function does approach negative 9.8, that horizontal asymptote, as t gets larger and larger. That equilibrium solution is stable. All the solutions approach it. It's attracting them. How do you do it? Let's just do 2 steps because it's too tiring otherwise. Over the time interval from 0 to 1, this is a time interval. I maybe should have written that in there. I won't bother retyping it. What's the step size? Delta t, it's the length of the interval, b minus a, all over the number of steps. So we get 1 minus 0 over 2, which is 1/2 or 0.5. Then the mesh points, just like with numerical integration, can be found by continually adding delta t. First to a, and then to t1, and then to t2, etc. So this is a right here. This is a plus delta t. This is a plus 2 times delta t, which is the same as b for this example because we're only doing 2 steps. This is our interval here. If you want to draw this, it could be helpful. Draw a line segment. 0 to 1, I'm breaking the interval up into 2 pieces of equal length. My mesh points are 0, 0.5, and 1. I'm not numerically integrating, though, because there's no integral. It's sort of an integration, because I'm kind of solving the differential equation in a sense, approximately. But let's not call it integration. What are the corresponding values of v1 and v2? And what would v1 and v2 be approximating? They would be approximating the function values at 0.5 and 1. I need the difference equation for Euler's method. Euler's method is a difference equation. We've talked about difference equations too. V1 is the starting value of V, V0, plus the change in V. The 0 here is not meant to say that this is a constant, so to speak. It's meant to say, in a sense, that's the starting change in V. The change in V is found by multiplying the rate of change of V with respect to t times the change in t. This is essentially distance, if you will. Change in V equals rate times time. Linear approximation. One of the main things to know from Calc 1. Replace V0 with 20. Replace delta t with 0.5. Do the math. You get about 5.1. Double check my numbers here. I actually did not take the time to double check these numbers. There could be mistakes. Do it again. V2 would be the previous value of V, V1, plus the change in V, which I'm labeling with a 1 just to emphasize that it's occurring at the next step, where we use a 1 there. This, once again, this change in V is the rate of change times the change in t. Distance as a distance change in V, that don't think too literally of the word distance there, equals rate times time. Plug the numbers and you get this. Again, double check my work. If I do make a mistake, I think as I post it, before I post this, I'll note any mistakes. Negative 2.35. How accurate is this? How far off are these numbers? In other words, what are the errors at each step? Error in all situations that I know of in math is always actual value minus approximate value, and it's very fortunate that this goes in alphabetical order. Actual comes before approximate. It's the way I remember it. So the actual value comes from the true solution, the phi function. The approximate value comes from Euler's method. So we know the true solution, so we can find the errors here. Here's our true solution. Plug in T1, which is 0.5, I get about 8.27. Plug in T2, which is 1, I get about 1.16. You should double check those numbers. Compare to V1 and V2 that I got from Euler's method. The error at step 1, E1, this is not the number E, it's not 2.718, it's error at step 1. Actual value minus approximate value, which is approximately 8.27 minus 5.1, 3.17. Not too small, we'd like it to be smaller than that. And the error at step 2 is even bigger. E2 is actual minus approximate. 1.16 minus negative 2.35 is positive 3.51. It's getting bigger in absolute value. Errors can be negative. If the approximate value is too big, then this difference would be negative, and you want to keep track of that kind of thing. And finally, we can make a graph. Typically, the errors get bigger with each step. That doesn't always happen, but typically. Make a graph to illustrate this, and this will be our last slide for this lecture. The red graph is the solution for the initial value problem. That's the exact graph, so to speak, exactly following the slope field. The pink graph is it's a graph I could make from the data that I get from Euler's method. V0 is the second coordinate at this point. V1, 5.1, is the second coordinate at that point. The true value is closer to 8.27. V2 is negative 2.35, the second coordinate at that point. The true value of the function of the solution to 1.16 here. These vertical distances here and here are the errors. And they are positive because the actual value is above the approximate value in this case. I connected the dots with straight line segments. That's just a natural, easy thing to do. You don't have to do that, and there are good reasons to not do that when you're doing high precision numerical computation. Though, if you were doing such computer work, you wouldn't be using Euler's method, actually. You'd be using a higher order method that would be better. Something that comes to mind is something called the Runge-Kutta method, if you want to look that up. To give you a better method for one thing, and also you'd probably connect the dots with some sort of smooth curve with an interpolation method. That's the end of lecture 5A.